Perfect. All right, here we go. So if we're going to graph polynomial functions, these are a list of things that they're going to ask you to be finding or doing on your homework. List each real zero and its multiplicity, the number of times it's repeated as that zero, as that x-intercept. Determine whether the graph crosses or touches at that x-axis at each x-intercept. Determine the maximum number of turning points. That has to do with the degree. Determine the end behavior, that is, find the power function that the graph of f resembles for large values of absolute x. And then sketch the graph using those zeros, the multiplicity, and the end behavior. All right, so the first things first. If we're going to graph this function, first we're going to find his x-intercepts, his zeros. Lucky for us, it's already factored. My mom is here. Just give me 1 second, guys. I'll be right back. Michael, hang tight. All right. Okay, she's like 30 seconds away. All right, so it's already factored. So if we set each factor equal to 0, we would have, remember, this is x minus 3 to the third power. So there's 3 factors of x minus 3. If it helps you to see all 3 of them, please don't be afraid to do that, okay? All right, so I set this equal to 0. I get x equals 0. I get x equals negative 2. And I get x equals 3, 3, and 3. All right, they want the multiplicity. This was an x-intercept or a 0 one time. So he has multiplicity 1. X equals negative 2, 1 time. So he has multiplicity 1. X equals 3 was a 0 3 times. So he has a multiplicity of 3. So now they want to know, is it going to cross or just touch the x-axis? Well, remember, odd multiplicity is going to cross the x-axis. So that's going to be a cross point. Odd multiplicity will cross. Odd multiplicity, but remember, it's a higher odd multiplicity. So the higher it's repeated, the more of that flattening out effect it's going to have. So again, it's going to cross, but I say that it kind of sits, and you'll see what I mean as it crosses. It's going to have this flattening out effect. All right, time out, she's here. Oh, that's much better. Guys, I am so sorry this is so chaotic. That was so my bad, but I'm good now. All right, here we go. So now we know it's going to have this flattening out effect, but it'll still cross the x-axis. All right, they want you to determine the maximum number of turning points. Well, remember, the maximum number of turning points is always 1 less than the degree. So we're going to need that leading power function to know the degree of this polynomial. So guys, in order for you to know the degree, you usually need it in standard form, which means it's all multiplied out. But we don't need to do all that. All we really need is that first term. So just distribute the beginning of each parenthesis. So negative x times x times x times x times x. That would have been negative x to the what? 1, 2, 3. What did I do? 1, 2, 3, 4, 5. That, no matter what, will be your leading power function. If you were to have multiplied this polynomial out, that would have been the first term, which means it's a degree 5 polynomial, which is odd, and the leading coefficient, the LC, is negative. That's all we need to know. We can literally create the whole graph knowing this information now. So guys, if the degree is 5, that means the max TPs is 4. The maximum number of times this graph can turn and change direction from increasing to decreasing or decreasing to increasing is 4 times.
The TP is turning points.
Turning points, max TPs. All right, so guys, now the end behavior. Let's get all this on a graph so we can fill in the graph. We have x-intercepts at 0, -2, and 3. 0, -2, and 3.
Miss Hardy,
Yes.
wouldn't the maximum turning point be the same as the degree number?
No. If it would turn another time, you would have a 6th x-intercept. And you can't have more intercepts than the degree. So the max turning points is always 1 less than the degree.
Then what was the one that's equal to the degree?
The number of x-intercepts is equal to the degree. So technically, I have 1, 2, 3, 4, 5 x-intercepts to my degree 5 polynomial. Do you see that, Jay?
Yes.
Okay. All right, so here we go. So they want you, instead of having to plug numbers in and create more points, you should have enough information to go off of to create this graph. Guys, if this is a degree 5 polynomial, that's an odd polynomial. What's the end behavior of an odd polynomial have to be? Opposite. One end up and one end down. If the leading coefficient is negative, which end do we know is up? Think about a straight line with a positive slope. It's up on the right and it's down on the left. So to the end, to the right of your last x-intercept, your graph has to end up on the right. And to the left of your last x-intercept, your graph has to end down. So just give yourself targets. All right, we know that according to the behavior of the multiplicities, every single x-intercept creates a cross. So we should be able to fill the graph in without having to plug any other numbers in and create any more points. So I know the graph has to end down here, right? So start down here and head towards the first x-intercept. -2 had a multiplicity of 1. Guys, that's just a normal cross. Cross right over the x-axis. All right, what is your graph eventually going to have to do at some point in order to get to the next x-intercept? It's going to have to turn and come back down. So make it turn. It doesn't matter. I could have gone up here and make it turn. You could have made it turn down here. The good news is we all have positive y values for this interval of x's. That's all that matters. We don't care how big they are. We just know they're positive y values. All right, so I turn. I head towards the next x-intercept. Guys, x equals 0 was a multiplicity of 1. That's a normal cross straight through. All right. Eventually, what is my graph going to have to do to get to the next x-intercept? It's going to have to turn at some point. And again, I don't care where. If my graph goes this low and your graph goes this low, who cares? We're still showing that this interval of x values creates a negative y value. And that's the only thing we care about. So we turn back up. Now, guys, if you notice, x equals 3, that was a 0 3 times. So the multiplicity is getting higher, which means it's going to create that flattening out effect as it crosses through that point. But it's still going to cross. That's the important part. So as I approach it, the graph should start to flatten a little bit and then pass through. But it still passes through. And then there's the graph of your polynomial. So again, it's supposed to be quicker than you having to plug in a number out here, get an official point. Plug a number in here and get an official point. It's just quicker. As long as you know all of this information, you can create the graph yourself just based off of the end behavior and the x-intercepts. Everybody okay at home? Are we all right? Yes? Good question. Go ahead, ask me, Sky. No question? Oh, sorry. I thought you had a question. All right. Thank you for forwarding me. All right. Here we go. Let's do this one. So if we set this equal to 0 and solve, right? Let's get our x-intercepts. Guys, I have a factor of x plus 3 2 times. So if you want to write that to remind yourself you're going to get 2 x-intercepts, please do so. You also want to be careful when you go to get your leading power function. You want to recall that that's 2 factors. So when you go to multiply your fronts, you don't forget that. All right. And then I have, let's set our factors equal to 0. 2 gets set equal to 0. I don't get anything from him. I just always do that so I don't forget. If he has an x, I'm going to get a 0 from him. All right. And then I get what? X equals -3 and -3. I get x equals 1. And I get x equals 4. So I have 1, 2, 3, 4 x-intercepts technically. All right, if you want, throw on a graph right now. We can do this as we go. start looking at the crosses and touches. Guys, this has a multiplicity of 2. Even multiplicity just touches the x-axis. It doesn't cross. That's a bounce or a touch. All right, x equals 1 was multiplicity 1, and x equals 4 was multiplicity 1. So those are just normal crossovers. A normal x-intercept, odd multiplicity 1, that's just a normal cross. Okay? All right, well, in order to get my turning points and the end behavior, I need that leading power function. If this polynomial was all multiplied out, who would have been that first term? Well, guys, just multiply your fronts. 2 times x times x times x times x. That would have been a 2x to the 1, 2, 3, 4. Guys, that is your leading power function. If you had multiplied that all out, it would have led with a 2x to the 4th, which means it's a degree 4, hence my 4x intercepts. All right, its leading coefficient is positive, and the max number of turning points, the max number of times it could turn and change direction, well, if it's degree 4, then the max is 3. It could turn 3 times. All right, let's do our end behavior. Our end behavior, the degree is even. Even degree polynomials' end behavior has to be the same. So both up or both down. If the leading coefficient is positive, it's both up. So to the left of my last x-intercept, my graph has to end up. To the right of my last x-intercept, my graph has to end up. And now you should be able to fill the graph in just based off of when it crosses and when it touches. So let's start up here and let's head towards that first x-intercept. All right, guys, -3 had a multiplicity of 2, which means it doesn't actually cross over the x-axis. It's just going to touch it and bounce back right in the direction from which it came. So I'm going to hit it and bounce and go right back in the direction from which I came. All right, then what's my graph going to have to do at some point? It's going to have to turn to head towards the next x-intercept. So at some point, make it turn. That had a multiplicity of 1, so that's just a normal cross. Then what is my graph going to have to do to head to the next x-intercept? It's going to have to turn back up. So at some point, make it turn and come back up. And then this was a normal cross, multiplicity 1. So just let it cross, and it ends back up. So again, we don't actually know any official y-coordinates, but we don't care. The only thing we ultimately care about in upper level math is we now know that this interval of x values make a positive y come out. These interval of x values make a positive y value come out. This interval of x values make a negative y value come out. And this interval of x values makes a positive y value come out. We don't actually care what y value though. We just care if it's positive or negative. Where is the graph above or below the x-axis? Okay, is everybody okay? So like I said, last year, your teachers had you guys plugging numbers in on each interval and getting more official points. We don't need them. We just need these sketches. We need these quick sketches of the graph. All right, let's go to the next question. Mike, are you okay? Yeah. Okay. Okay. So if you're not going to be asked to graph the polynomial in this section, they're going to ask you to write the equation of a polynomial function given certain information. Now, depending on how much information you've given, you can either write a unique equation or a non-unique one, and I'll explain the difference. All right, so guys, if you're going to write the equation of a polynomial given its 0 or its graph, this is what you need to do. Identify your zeros and their multiplicities. I always warn you guys to watch out for the x-intercepts of 0, and you'll see why. You want to write the real intercepts or zeros in their factored form. So guys, this is what you're going to start each equation with this formula, if you will. And then you're going to determine or calculate a correct value for A, depending on whether you can write a unique or a non-unique actual equation. So let's give it a go. All right, so guys, they want you to find a polynomial function that will have zeros at -4, -2, and 3, and the degree of the polynomial has to end up being a degree 3 polynomial, all right? All right, so here we go. Take your formula, f of x equals a. Always start with that. If these are the zeros, then at some point they were factors of this polynomial expression. So now write your zeros back as factors. So guys, if you ended up with -4 as a zero, then he was a factor of who? X plus 4 or x minus 4? X plus 4. Because when I set it equal to 0, I would have gotten -4 as an x-intercept. All right, if I have an x-intercept at -2, then I must have had a factor of x plus 2. And then if I have an x-intercept at 3, I must have had a factor of x minus 3. Okay, so the only thing we need now is a number for a. Here's the thing. Do you guys agree? Don't write this down. Let me just show you. If you have a polynomial that has x-intercepts at -4, 2, -4, -2, and 3, isn't this the graph of a polynomial that has x-intercepts at -4, -2, and 3? Yeah. But isn't that also the graph of a polynomial that has x-intercepts at -4, -2, and 3? And then isn't that the graph of a polynomial that has x-intercepts at -2, -4, and 3? Yeah. So guys, when it comes to writing a unique polynomial expression, you need more information. If I'm going to make a unique value for a, I need another point that lives on this polynomial besides a 0. But they didn't give me that information. So if they're not going to give you more information about the line or about the polynomial, then you can pick whatever number you want for a, and it will still be a polynomial that had x-intercepts at -4, -2, and 3. So if they're not going to give you more information, have at it. Let a be any number you want. But if I could make a suggestion, the easiest number to let a be is 1. Because if you're going to have to multiply this out because they want the answer written in standard form, I don't think you should be putting your favorite number of 28 in front of the parentheses, and now you have to distribute the 28 in. So if I could make a suggestion, if they allow you to pick the a value because it's not unique, then I would just let a be 1. Now, if you are looking at the graph and all you can see are the x-intercepts, but if you saw that it was up on the left and down on the right, well, then you'd have to at least let a be a -1 so that the sign matches the end behavior of the graph. But if they're going to allow you to pick it, please pick 1, okay? All right, so now all you have to do is say that you're going to let a equal 1. And then it becomes f of x equals x plus 4 times x plus 2 times x minus 3. Now, guys, on your homework, there's a good chance they ask for the answer to be written in standard form, which means you have to FOIL it all out. I'm not going to do that. It wastes too much time. All right, let's do this one. Now we have to write a polynomial function who has a 0 at 0 with a multiplicity of 3. It has a 0 at 4 with just normal multiplicity, and it has to end up being a degree 4 polynomial. All right, guys, get yourself started. F of x equals a. That's how we start every single one. Now we have to start writing our zeros as factors. So I always say to watch out for the ones that have a 0 at 0, because who would you have had to have a factor of to end up with a 0 at 0? Anybody know? You would have had to have a factor of just x, and they always go in front. So if I'm going to have a 0 at 0, I must have had a factor of just x, so that when you set x equal to 0, you get 0. But guys, if it had multiplicity 3, how many factors of x did I have? I had 3, so that's x to the third. You must have had an x to the third to end up with a 0 at 0 with multiplicity 3. And then last, if I have a 0 at 4, then I must have had a factor of x minus 4. And now again, because they didn't give me any other information to go off of, since they didn't give me any other points that pass through this graph, I can just let a be whatever I want. I'm writing a non-unique equation. So I'm just going to let a be 1. And that would definitely multiply out to a degree 4 polynomial. Okay? Are you guys okay? Yes? All right. All right, I'm going to try and do this one, and then I might skip down to a graph, and then the bell's going to probably cut me off. All right, now we have to write a polynomial function with the given zeros, but they're telling you another path, a point that it has to pass through. So these are the types of problems where you're actually going to be able to get a very specific a value. All right, so let's get started. We have zeros at -2, 1, and 5. Multiplicity is normal. So f of x equals a times, I must have had a factor of x plus 2, normal multiplicity, so just one factor, x minus 1 and x minus 5. So that is a non-unique polynomial. I could let a be anything, and it would definitely end up being a polynomial with these 3 zeros. But now they've given us more information. Now our polynomial doesn't just have to have these zeros, he's also got to pass through this point. So when they tell you this point, now you can borrow this point as an x and a y value that you can plug in and solve for a correct a value. You're going to be able to get a unique a value specific to this polynomial function's graph. So let's plug them in. -5 in for y equals a times, I'm plugging 0 in for x. Right? So that's what? 2, -1, -5. All right, a times 2 times -1 times -5 is positive 10a. Divide both sides by 10. And we find out that a needs to be -1/2 in order to make that information true. So now you just pop them in and call it a day. Now again, I do apologize because I think there are definitely some homework problems where they're going to want this multiplied out. Okay, I'm going to skip this one, but I'll have it filled in on the actual written notes that I send you. Let me do one where they give you the graph, and then we can stop. You okay, Michael?
Yeah.
Okay. Does this ring a bell from last year?
I'm not very good at remembering.
Okay, here. I always feel like I shouldn't ask that, maybe.
Oh, wait, I wasn't.
It's going to be filled in, Michael. You have to get it off the filled in notes.
Okay.
I only have 3 minutes left.
No worries.
All right, so guys, look here. Let's say they give you the graph. It's the same process, except this time, you just have to identify the x-intercepts yourself. Now you can see end behavior. Like right now, I know a has to be positive. The leading coefficient better than positive to have a polynomial graph who ended both up. So if you don't know another point on this graph, you could literally let a be 1 because you know it was up. If they both ended down, then you would say, all right, I can at least let a be -1 because the end behavior is both down. So now that you're looking at the graph, you can get a little bit more specific with a if you don't know another point, just based off of the sign that he is going to need to be. All right, let's identify our x-intercepts. I have an x-intercept at -3. Guys, pay attention to how it crosses. It crosses like normal, so that must be multiplicity 1. All right, I have an x-intercept at -2. No, I'm sorry, -1. All right, but look how he behaves. At -1, what does the graph do? He bounces, which means the multiplicity had to have been even. So it must have been multiplicity 2, or multiplicity 4, or multiplicity 6. However, the book will tell you to assume the lowest multiplicity possible. So the lowest multiplicity possible would have been 2. All right, and then it crosses at x equals 2, and look how it crosses, like normal, straight on through. So that's a multiplicity of 1. All right, let's write it. So f of x will equal a. I didn't have an x-intercept at 0, so I don't need to just x. I'm going to need an x plus 3 one time. I'm going to need an x plus 1, and I'm going to need that to be squared because he had a multiplicity of 2. And then I'm going to need an x minus 2 like normal.
Miss Hardy.
Go ahead.
How did you know -1 has a multiple?
Because look how it behaved. It bounced. It didn't cross over. So we know that it had to have been even multiplicity to make it bounce. And you are instructed when you're writing your own equations to assume the lowest multiplicity possible. So the lowest even multiplicity is multiplicity 2. Okay? All right? And then, now here's the thing. Normally, they will label another point on the graph like they did here. So you are very sure that there's another point you know to go get an A value. Normally on this, it's not safe to assume any other points are known. But guys, it is clear as day that the y-intercept is 0, -3. I really wish they would have labeled that because I think it's confusing. Like, am I allowed to assume it's 0, -3? What if it's 0, -2.99999? So again, I feel more comfortable when they label it, but they don't always. But if you can see a clear as day other point, then you can solve for a more specific A value. Otherwise, I would have just let A be 1, knowing that it had to be a positive number. But because I can recognize that point, I'm going to plug -3 and 0 in, and I'm going to solve for a specific A value. And I'll have that filled in on the notes. All right, I apologize. 30 minutes is just not long enough, guys. Does anybody have questions for me?